Good afternoon. No, good evening. Good evening, you guys, or whenever you're watching this. Um, this is the video where I am going to go over all of the answers for the packets. Let's see. This is the first physics video I've done. I've been doing a bunch for 5th grade, but the first physics video I've done. So I hope you guys are doing well. I hope you're keeping healthy and staying inside and self-quarantining as much as possible, self-distancing as much as possible. Update on me, I'm working on my house, two doors down from Lisa. How are you, Lisa? Hope it hasn't been too loud for you. If I'm talking quietly, it's because it's 11:15 right now. I just got home about 20 minutes ago, jumped in the shower, and came down here. I've been working very long days. I'm just going to lean back here. You know what? Let's get comfortable. Been working long days, obviously doing school stuff as well, but working long days at the house. The house is coming along. It's just completely gutted now. I did well with my demo. Messed up today on something else, but that's a story for another time. I'm gonna redo all my work from today tomorrow, which is fantastic. As you can imagine, I'm recording a video now at 11:15 at night. How my day has been today, but that's not for you to care about. Let's see. What I would like to do, actually, I did a Google Hangout. I'm sorry, my screen's bouncing. I did a Google Hangout with my 5th graders today, and I think that would be fun for us to do. Productive at the very least, maybe not fun, but productive at the very least. In order to do a Google Hangout, you need to have a Gmail email address, and you do it through Google Chrome. It's an extension that you would add on to Google Chrome. All the 5th graders did it today. It was good. So maybe we can do that at some point. I'm sure. I know, Jody, you know how to do that. I hope your brother is doing it as well. I'm sure there are several of you that know how to do it. I'm sure, Josh, you know how to do that, no problem. So that'd be nice to do at some point. That would be nice, but that is, I think, the last update for me. I think that I'd like to do the Google Hangout at some point for the next chapter, but what we're going to do now is I'm going to go over the remainder of the answers that you guys submitted to me. And these are the last parts of the packet, and I want you to fix your answers. Make sure you have all good answers. If for some reason you were absent on a day, get the answers from someone in the class that you trust to have the right answers. And then you're going to resubmit them to me. Oh, by the way, Josh, I love the way that you submitted it as a one scanned PDF. Oh, it's beautiful. Josh has, it was just one file. A lot of you guys are taking pictures, which is fine. We get a picture for every single page, which means I have to reorganize them and rename each one of them, renaming each one your name and then what numbers it is. And it's just organizing, takes extra time. If you can do what Josh did. I think I'm assuming you scanned the whole thing, Josh, as one. Oh, magnifico. Or either that or you took pictures and you just made it into one PDF or something like that. However you did it. Oh, beautiful. Anyway. Let's get to the answers. I'm tired, can you tell? I know 11:15 isn't late for you guys, but because you guys probably sleep till noontime. I'm assuming this is just going to be super boring. I should throw like random things in to keep you guys on your toes. Clementines for eyes. If somebody doesn't know what that means they didn't watch the video. Oh boy, where do we leave off? Chapter 13. I think we left off right at number 46, chapter 13. Some of you didn't submit 46, some of you did, whatever it is. But I think we left off last time we were in class right at chapter 13, which is number 46. So let's see what you guys had. For number 46, it said, talks about states of matter. It said, fluids are defined in the book as materials that flow and have no definite shape of their own. Using this definition, state whether each of the materials below are fluids or not. Now, the key here is knowing the difference between a fluid and a liquid. A fluid, liquids are fluids, but liquids aren't the only fluids. Remember, it's anything that flows. So a solid generally would not be a fluid, but a liquid or a gas could be a fluid because they can flow. So you would have to write on here, and water is, and so you write F if it's a fluid, and if it's not, water is a fluid. Orange juice is a fluid. They can flow. You can pour them out. Gravel is not a fluid. Although you could get a bucket of gravel and pour the bucket of gravel out, it doesn't flow as one continuous thing. Molasses is a fluid. Even though it's very, very viscous, meaning thick, it still does flow. If you pour it out, it still does pour out, although its fluidity is very low because its viscosity is very high. Air is a fluid. And sand is not a fluid. That's a tricky one because you can pour sand out and it looks like it can flow like that, but doesn't, again, flow as one unit. It's individual particles. I mean, you could take, I don't know, I'm looking at a refrigerator right now. You could take refrigerators, and if you had a big enough bucket of them and poured them out, you could make them pour out. Just because something pours out doesn't mean it flows. Sand does not flow continuously. It is not a fluid. Let's see what we had. I'm going to be yawning a lot through this video. I apologize. Jake, you got it right. FFN. Let me find Jason. Jason, yours is the craziest as far as trying to figure out which part you have. FFN, FFF. Oh, so Jason, you said sand was a fluid. Sand is not a fluid. Let's look at the next person. Hope. Can't really see yours. I can just see B, C, E, and F, but it looks like you have orange juice as a fluid. Air is a fluid. Gravel is not. Sand is not. You're correct. Jody, I can't really read yours too well because for some reason yours is very poor quality, but it looks like you had water and orange juice are correct. Gravel is not a fluid. You're right. Molasses is a fluid. They said air is not a fluid and sand is. I'm assuming you thought that fluid meant liquid, so change that. Air should be a fluid and sand should not be a fluid. Who's next? What else do I have here? Lisa. Lisa, you are correct on A through D and F. E is wrong. Air is a fluid. You have it as not. Gisele, you are correct. Josh Shepida. Let me scroll through this. Josh, you are correct. Jillian. Oops. Oh, I have everything in the wrong order from Jillian. That stinks. Why do I have everything in the wrong order from you? It's probably my fault. I don't have that page from you, Jillian. I'm sure you gave it to me. Let's take a look. Let's see, you gave me 6 pages, and I have 1, 2, 3, 4, 5, 6. You didn't give me that page, Jillian. You gave me 41 through 45, and then you gave me 41 through 45, and then you gave me 57 to 59, but you did not give me that page. You don't have to give it to me now, just, give it to me when you are. There's a fruit fly around here. Give it to me when I got him. Ugh. I'm tired. Jillian, give it to me when you are submitting the full thing, but make sure it's right. So 46 was FFN, FFN. What is the SI unit for pressure? Let's see what you guys have for answers. Can't look at Jillian's because you didn't turn that page in. Josh, you have Pascal, which is correct. Jocelyn, Pascal, Pascal. I'm seeing a lot of Pascals here. Good. The SI unit for pressure, Jason, is pressure. No, but you corrected it. You put Pascal afterwards, so you're correct. Good. You guys all look like you have the right answer. Pascal, which is abbreviated capital P, lowercase a. 48, what is a unit for pressure expressed in base units? Let's see if anybody get that. Hope, I'm looking at yours first. Newtons per meter squared. You are correct. Let's see. Jason, you have the unit for pressure expressed in base units as pascals. No, pascals expressed in base unit are not as pascals. They are newtons per meter squared. So fix that, Jason. Jake, you have newtons over meter squared, but you have a lowercase n. It should be uppercase n. There is no lowercase n that we're talking about. Lisa, newtons per meter squared. Yep. Jillian, I don't have that page. Josh, you are wrong. You have the equation for pressure as force over area. Now, you are correct that that is the equation for pressure, but that's not base unit. Base units would be newtons over meters squared. Actually, that technically, it's not base units. I should have, that was my poor wording of that question, because it should be what is a unit for pressure expressed in regular units, because newtons isn't base units. It would be kilograms times meters per second squared over meters squared, and I just can't do that in my head right now. But anyway, you know what I mean. Jody, you have it correct. I was looking for newtons times meters squared. Newtons over meters squared. 49. The term PSI was thrown around a few years ago when a certain local QB, not local anymore. I'm sorry, Jillian. Was incorrectly, well, hey, now he's at Tampa Bay. Who knows? Maybe he did deflate those footballs. I didn't. Anyway, the term PSI was thrown around a few years ago when a certain local QB was incorrectly accused of doctoring the inflation pressure of a football. Explain what PSI stands for and how is a unit of pressure using the base units from above. How it is a unit of pressure using the base units from above, or the equation for pressure. Well, PSI stands for pounds per square inch, and it's a unit of pressure because what is pressure defined as? As Josh had in his previous answer, it's defined as force over area. That's force is the newtons, area is the meters squared. And the word pound is an English system unit for, it's the same. It's like the equivalent of newtons. Newtons is metric though, and pound is the customary system or English system. And the word square inch defines a two-dimensional area. You could have square feet, square miles, square whatever. And so, just like, you know, cubic whatever is volume, square something, or acre squared is area. So you have pound per square inch. You have pounds on top. Per means divided by, and square inch on the bottom. So you have a unit of force divided by a unit of area, which is length squared. The word per is division sign that tells us a division problem that matches up with the equation for pressure. So PSI, pounds per square inch, matches up with the units for pressure. Let's see what you guys have. It's a tricky one, so I don't know if you guys would have it correctly. Jason, pound force per square inch. Okay, you wish to have been a little bit more descriptive. Hope, PSI equals pounds per square inch, pressure equals force to over the surface area. Yep, you're right. Jody, this is very fuzzy. PSI pounds per square inch, and PSI equals something newtons per meter squared. Pressure when force of 1 pound is applied to the area of one. Okay, that's okay, Jody. Josh, you put pound per square inch. You expressed what PSI means, but you didn't answer the second part, Josh. Unit. How is it a unit of pressure using base units from above? Gillian did not have that problem. PSI stands for pounds per square inch. The equation for pressure. I'm assuming you guys that are getting it wrong are just getting it wrong because I didn't have the word "it" in there, which is not descriptive enough. Lisa, pound force per square inch. Yeah, PSI is a pound force per square inch, or the pressure resulting from a force of 1 pound force applied to one area. Yeah, Lisa, I like your definition. Good. Jake, PSI is pounds force per square inch equals a pressure equation, which is force over surface area, and PSI equals pound force over inches squared, which is the same thing. Good, Jake. All right, good. Next one. This is going to be a long time. I don't mind if you guys come back and watch this in just little increments. 50. A rectangular box is placed on a table. Actually, let me make sure this is still recording. That would stink. Yep. Wow, 17 minutes so far. Oh my gosh, I'm sorry. A rectangular box is placed on a table so that its largest surface is resting on the table. Okay? Picture a rectangle. All right, let's make this the rectangle. This would be its largest surface here. Boom, like that. Okay? This is a very flat rectangle, but rectangle nonetheless. Let's see if I have any different rectangles. This is Charlotte's homemade xylophone. As I play it for you. Very nice, right? Anyway, that would be like this. Not like this. Not like this, but it'd be placed like this. Where's my paper? Okay. Then it's rotated, so its smallest surface is resting on the table. It should be a question mark there. Period. What has happened to the pressure? Okay, so pressure here compared to here. Okay. What has happened to the pressure? Did it increase, decrease, or stay the same when the box was rotated? Explain what this is. The pressure on the table increased. You know what? From now on, I'm just going to basically do quick looks at everybody's stuff. I don't want to try to increase the time on this. Pressure on the table increased when the box was rotated, so it increased because though the weight of the box stayed the same, the surface area of the box decreased. So you have the top part of that equation, the F stayed the same. I don't know what the weight of the box is. You make it whatever you want. But the surface area decreased, which means the weight per square area decreased. All right, 50 for Hope. It decreased because its surface area decreased. Okay, so when you think, it decreased because the surface area decreased, that's fine. But what you're doing is you're dividing by a smaller number. When you divide by a smaller number, it makes your final number bigger. Think about, 20 divided by 2. 20 divided by 5 is 4. 20 divided by 2 is a small number, but it equals 10. So when you divide by a smaller number, you get a bigger answer. Hope, so fix that, Hope. Jake, you're right. Jason, I have no idea where yours is. Let's see. Lisa, increases. Yep, Lisa, you're right. Gisele, you have the same problem as Hope. You got to fix that. Jillian, I don't know where yours is. Josh, increase the area smaller. Yep, you're right. Jody, pressure increased on the same amount Yep, you're right. Jason. The gas particles will shift, but the weight or shape of the box does not change. Yeah. So unequally in boxes, pressure increases, but not across the whole box. Okay, I guess you're right around there. Right, the answer is fine. All right, that's everybody. Next, 51. Using the equation on page 342, find the pressure for the following problem. 156 Newton boy sits on top of a 5 Newton bucket with an area of 0.8 meters squared. What is the pressure on the floor? Let me show you. 201.25. 1 second. And though you may wonder, I'm not editing this video. I don't have the time, so this is a one-take kind of thing. 201.25, you get that by taking the force, which is 156 plus 5, 156 Newton boy, plus a 5 Newton bucket, you just add them together. So that's a total force, divided by the area of 0.8, and you get 201.25. I don't know if you guys got that. Hope you forgot the bucket. Jason, you got the wrong answer. Kilopascals. I don't know what you did. Jody, yep, you got the right answer. Josh got the right answer with no work. Jillian, I don't know. Giselle, okay. Oh, Giselle, you multiplied the boy times the bucket. You don't multiply them together. They're just both there, right? They're both sitting on top of the bucket. I mean, the boy and the bucket are both on the floor, on that area of the floor. You don't multiply them. You just add them together. Lisa. We said 166 plus 5 equals 161. Good. Then you divide by the area of 0.8, but you didn't do that. And you put two answers, either 251 or 201, to 201.3. Pick the second one. I don't know how you got those. Oh, because one you multiply? I don't know what you did. It's 201.3. That's the answer. Pick. Jake, you got the right answer, and that's everybody. 51 is good. 52. Using the equation on page 342, find the pressure for the following problem. A 150 kilogram man standing on his back porch decides to stand on 1 foot. I don't know why. His small shoes, little tiny feet, I guess, create an area of 21 centimeters squared. The deck can only hold 6.4 kilopascals of force. Will the porch be able to hold him? No, it cannot hold him. What you have to do there is, you see 150 kilogram man, you have to convert that to newtons, and the area is 21 centimeters squared. You have to convert that to meters squared. So how you do that is 21 centimeters squared is 0.21 meters squared, and the 150 kilograms, when you multiply by 9.8, because you have to convert the mass into weight, which is a force, multiply by 9.8, it becomes 1470. Then from there, it's just 1470 divided by 21, and you get 7,000 pascals. Now they give you the answer in kilopascals, so you move the decimal point 3 places to make it 7 pascals, and so his 7 pascals is 7 kilopascals is over the 6.4 kilopascals of force. That porch, he's going right through that porch. If you didn't follow that, this is the work right there. Compose it on your screen, and boom. Yep. Next, this must be so boring. I'm so sorry. I don't even know if you guys got that. I'm not going to waste my time going through. You guys fix it if you didn't get it. 53. Using the equation on page 342, consider this scenario. In a tornado, the pressure can be 15% lower than the normal atmospheric pressure. This is actually true. Not that I would put a lie on there. I don't know why I had to say that, but in a tornado, the pressure can be 15% lower than normal atmospheric pressure. And the normal atmospheric pressure is 1.0 times 10 to the 5th pascals. It's basically 10,000. It's late, man. 10,000 pascals. Suppose a tornado occurred outside a door that was 195 centimeters high and 91 centimeters wide. Right away, you should be thinking, I got to change those into meters. Move them over 2 decimal places. So instead of 195, it's going to be 1.95. Instead of 991, it's 0.91. What force would be exerted on the door from the inside of the house to the outside? Because remember, I said the tornado caused there to be less pressure. So there's going to be an outward pressure because there's more of an inward pressure from inside the house. That's why there's an old wives' tale that you should open your windows during a tornado. Did I make a question mark on here? No. There's an old wives' tale that you should open your windows during a tornado because there's less pressure on the outside of the house than there is on the inside of the house. It's based on good science in that, yes, there is less pressure outside the house than there is inside the house. However, the idea of the pressure isn't the thing that is going to be the most dangerous. The thing that's going to be the most dangerous is the tornado. And if you have your windows open, they can take some sort of brunt of maybe some dust and sand and things flying against them. If you open your windows and just have big gaping holes in your house, you can have all that stuff flying in your window. Okay, yes, there is a pressure differential, but you don't want all that junk flying in your window. Anyway, it's asking what force would be exerted on the door from the inside to the outside. And so you take the force divided by the area. Well, they give you the pressure this time, and they don't give you the force. It's asking for force. So you flip it around, make it force equals pressure times area. Okay, and well, to get the area, you multiply the width times the height of the door, 195 times 91, or you've got to convert them to meters, 1.95 times 0.91, and then you take that number and you multiply it by the pressure of, here's what it is. Sorry, you don't do that yet. So let me just show you. So we have to find what normal atmospheric pressure is. So what you're doing here is this top line, pressure equals force divided by area. That's our normal equation. Then we force equals, that's rearranged for force equals pressure times area. Area equals width times height. So that's how I find my area. So that's my area inside of, that's my area of my door. Okay, 1.7745. Now, P equals 0.45 times 10.10 to the 5th. What that is doing is that is telling you what the pressure is outside. Okay, so you have the pressure outside versus the normal atmospheric pressure inside. So you get right there a pressure difference. Okay, that's what you're getting. So you have there, and then you take the final equation, force equals pressure. Area times pressure. This is your area, this is your pressure, and you get your final total. That's how you do it. Let me see if anybody actually did get that right. I doubt you did. But let's try it. Let's see if anybody got it right. Hope. Nope. Jake. Nope. Jason. Nope, not Jason. Where's next one? Lisa. Lisa. No, but your answer looks like it could be close. But no, it's not. Giselle, nope. Jillian. No, Jillian, I still don't. Where's yours, Jillian? I think you submitted 65 a couple different times. No, Jillian, I don't know where yours is. I think you missed 2 pages for me. I think that's everybody. Oh, Josh, did you get it? You did not. Okay, so the key that I think everybody's missing is the pressure difference there, which is what I got in that second part. Understand that? It's a tricky one. That one was tricky. Very, very, very tricky. Number 54. 30 minutes in. Oh my gosh. If 1 pound is 4.4 newtons, how many pounds of force would your answer in the previous problem be? Obviously, you can only get the correct answer if you got the correct answer. So here, you just take your previous answer, what should be the previous answer of 26,617.5, and you divide that by 4.4 to get 6,049.4 pounds. 6,049.4 pounds of force. 55. Using the equation on page 342, find the pressure for the following problem. A car tire makes contact with the ground on a rectangular area of 12 centimeters by 18 centimeters. Again, jumps out to you. I got to convert that. If a car's mass is 925 kilograms, what pressure does the car exert on each of the 4 tires? Okay, so basically for the strategy for this one is, I think I'm frozen right now. The strategy here is you multiply 12 times 18, or 0.12 times 0.18, and you get the area of each tire. The car's mass is 925 kilograms, so you take 925 kilograms and you multiply by 9.8 to get the force, and you get 9,065 as the force, divided by the area, which was 0.12 times 0.18, and you get 2.16. Let me just check that. Let me see if I get the right answer here. I don't know if that's right. 0.12 times 0.18 equals, no, that should be, I have this wrong here. It should be 0.0216. So that's why I was going to say it didn't look right, so I'm going to do it right now. 965 divided by 0.0216 equals 419,975.9. And then, so you take that big answer, that the total amount of pressure that the car is having on the ground, but you have to divide that by 4. Divided by 4, your answer should be 104,918 pascals. Or, if you like, you can move it over 3 places and make it kilopascal. So instead of 104,918.98148, you make it 104 kilopascals. I don't know if I'm frozen or not. For some reason on my screen I'm frozen, but I'm going to keep going. If for some reason I'm not frozen, here's the work. Hopefully you can see that. You know what? Why don't I stop here? I've tortured you enough. And if this isn't working, then at least you'll have some of them instead of me wasting the rest of my time. I'll record another video with the rest of them.